Welcome everyone to the presentation of enabling run slicing through carrier aggregation in mmWave networks. I am Pagin, and today I will briefly describe the work that me and my colleagues have carried out. This talk is outlined as follows. We'll start with a description of our contributions and motivations, where we'll highlight the novelties of our work compared to the state of the art. Then our proposed algorithm is going to be presented, showing a comparison of its main novelties compared to the usual 5G architecture and protocols. Finally, the presentation will be concluded by describing how we simulated such protocol in the simulator NSPRE and by showing the results that we have obtained. So, one of the novel services that 5G networks will have to provide is the support for a vast and heterogeneous set of traffic specifications presenting different quality of service requirements. The achievement of such target is somewhat primitive using conventional architectures that are based on a one-fits-all paradigm due to the contrasting nature of the QoS requirements. Specifically, in this work, we target the successful coexistence of eMBB and URLC flows, the first requiring massive data rates, the latter depending upon high reliability and extremely low latencies. Network slicing, namely the concept of running multiple logical networks upon the same shared physical infrastructure, is deemed to be the key enabler for the support of such vastly heterogeneous traffic types. By analyzing the literature on such topic, we found out that most of the available works either focus on sub-6 GHz frequencies or study core network approaches. Compared to these research trends, our work focuses on mmWave frequencies and achieves network slicing using a radio access network approach, specifically using carrier aggregation. Going more in detail, the former term refers to the usage of the frequency bands which are located approximately between 30 and 300 GHz. This portion of the spectrum has been previously neglected due to its harsh propagation characteristics and its susceptibility to blockages. But thanks to recent advances in RF technologies, coupled with the usage of techniques such as beamforming and MIMO, we have finally managed to overcome these issues and to be able to exploit the vast amount of unused bandwidth that mmWave offers. The latter term, carrier aggregation, refers to a multi-connectivity technique at the MAC layer that provides service across multiple links called component carriers, possibly exhibiting very different central frequencies and with independent modulation encoding schemes and retransmission processes. First of all, this strategy allows to exploit a newly introduced macro diversity, since the different carriers can have different frequencies. Additionally, the use of carrier aggregation allows, in principle, to perform flow isolation on the different CCs, and to use for each of them ad hoc phi and MAC layers parameters that are targeted to the specific flow's QoS requirements. In order to explain our proposed algorithm millislice, we'll first take a brief look at how carrier aggregation usually works. So, starting from the upper layers, in a 5G cellular network, we usually have one or more data radio beaters, which are essentially end-to-end traffic flows, and each of these beaters is mapped to a specific PDCP and RLC instance. Periodically, these RLC instances notify the content of their buffer via buffer status reports, which are then usually forwarded to the MAC layers of the different carrier components. Once that happens, the usual scheduling is undertaken within the different carriers' MAC instances. What we propose is to modify the buffer status reporting procedure, tailoring the forwarding of such messages to the specific carrier's characteristics. For example, a component carrier located in the lower end of the spectrum provides a natural fit to URLLC flows, since it exhibits low isotropic losses, which in turn result in high reliability and consequently smaller delays. On the other hand, mmWave flows are possibly better suited to carriers located higher up in the spectrum, since it might be difficult to find the significant amount of needed bandwidth in the already congested lower frequencies. Even though this notion can lead to the intuition that performing a static orthogonal association between flows and carriers may be a good idea, this strategy actually leads to inefficiencies, mostly due to the significant difference between the URLLC and mmWave data rates. Therefore, we introduce our mmSlice, a dynamic cross-carrier scheduler located at the component carrier manager. In essence, mmSlice performs an association between a given data rate repeater quality class identifier and a primary carrier, followed by one or more secondary ones. Such flow will then be predominantly served by its preferred carrier, with the optional help of the additional CCs, subject to the following condition: the flows that favor such component carriers must not exhaust their primary resources. Specifically, as we can see in this flowchart, in the case of coexisting mmWave and URLLC flows, the mmWave BSRs will be redistributed towards both its primary and secondary carriers if and only if the URLLC RLC buffers contain less data to transmit than a predetermined threshold REMBB. In such case, each BSR will indicate a portion of the original size. Otherwise, the mmWave BSRs will simply be forwarded to such flow primary component carrier. And URLC traffic will be also served in the same fashion, simply by swapping their respective roles in the algorithm. The algorithm that we propose has been implemented in the simulator NS3, considering in such regard the mmWave carrier aggregation module as the starting point. Furthermore, the NS3 mmWave module and its mmWave channel model have also been employed, since they provide an accurate modeling of the involved physical phenomena coupled with a 3GPP like new radio stack for both GMBs and UEs. In order to carry out performance evaluation of mmSlice, we also implemented a simulation script that models a dense urban scenario that consists in a single GMB surrounded by a fixed amount of UEs that move within its coverage area. These users are then connected either to a EMBB or a URLLC remote host modeled as a UDP application with a specific data rate. By the way, in case of interest, the code is publicly available on GitHub. Then, in order to benchmark the performance of mmSlice, we use the following two baselines: a single carrier setup with no carrier aggregation, named thereafter NoCA, and a configuration with carrier aggregation and an orthogonal static association between flow QCIs and component carriers that is referred to as CA primary only. Regarding the simulation parameters, the system is configured to operate with a component carrier CC0 located at 28 GHz, and the system has a total amount of 500 MHz of bandwidth. When carrier aggregation is activated, an additional carrier CC1 at 10 GHz is used, and in such case the fixed total system bandwidth is split between the two carriers. Following the previous reasoning, the CC located in the lower end of the spectrum is set as primary for the UR-LLC flows, while CC1 is associated to the mmWave ones. Finally, we want to highlight the choices of R-mmWave and R-URLC of respectively 0 and 1. Using these values, we have that CC1 is never used for the UR-LLC flows, and it also results in spreading the mmWave traffic load upon both CCs if and only if there's no actual UR-LLC data in the corresponding RLC buffers. Regarding the metrics, we focused on average throughput, packet loss, and end-to-end delay at the up layer. And additionally, in order to capture the capability of a given strategy to efficiently make use of the available resources, we also introduced the carrier utilization efficiency metric ETACC. Such metric is defined as the amount of effectively allocated OFDM symbols over the total available ones, weighted by the specific carrier bandwidth. We now conclude this presentation by showing a brief summary of the obtained results. First, we take a look at the system performance as the mmWave traffic data rates varies. Focusing on the URLC delay only, on the top plot, we could say that millislice is the second best solution, significantly outperforming the non-CA case, but not by matching the CA primary only configuration. On the other hand, if we take a look at the average mmWave data rate that the system is capable to sustain, immediately notice that CA primary only is capable to beat millislice in the delay metric, only at the cost of strikingly low performances in the throughput domain. In fact, with respect to the mmWave QS requirements, millislice is the clear winner. Furthermore, we stress that the goal is the joint performance of the different flows, and in such regard, the dominance of the proposed strategy is quite pronounced. The carrier efficiency metric plot explains why this is the case. The static association between QCIs and component carriers performed in the CA primary only case leads to a severe underutilization of CC0 due to the very heterogeneous data rates of the different traffic specifications. On the other hand, millislice manages to exploit the bandwidth at its disposal in a significantly better manner. Finally, we have here the behavior of the system as the amount of mmWave users varies. For the delay, we have once again that millislice is slightly worse than the CA primary only configuration, but it considerably outperforms the non-CA case, since it exhibits delays up to 40% smaller than the latter. More importantly, as we can see in the bottom plot, millislice once again provides the best URLC and mmWave joint performance, since it is the only solution capable to deliver an aggregated system throughput in the order of gigabits per second, while satisfying the strict delay constraints posed by the URLC flows. So the key takeaway is that even though millislice is a simple heuristic policy, it still manages to jointly satisfy the contrasting QoS requirements of mmWave and UR-LLC flows. Therefore, achieving netto-slicing via carrier aggregation can be an interesting and promising strategy that allows to exploit the macro diversity that millimeter waves can offer. Finally, we reserve the study of inter-CC schedulers and joint ad hoc scheduling algorithms at the MAC layer for future work. This concludes the presentation of enabling RAS slicing through carrier aggregation in millimeter wave networks. So I thank you for your attention, and I refer you to the Q&A for eventual questions and doubts regarding our work.